Merry Christmas, people. This is Jose Abel, civil engineer, and I want to wish you a happy 2026, which is gonna be the year of the explicit solver. The explicit solver is gonna be what's gonna allow us to move into the next level of really huge simulations in OpenSees. We want to go huge. We want to go big in 2026 for our simulations. And explicit solvers are what's going to allow us to do exactly that. So what are these explicit solvers? So the explicit solver is basically the idea, imagine that you're hurling a rock and you are hurling it with a force of F, and you want to know what the acceleration is of that. That's an A, by the way. So you know that Newton, F equal ma. And even Mr. D'Alembert said F minus ma equals 0 and recast every dynamics problems as a statics problem. But that's getting out of the way. The explicit solvers take this idea, which allows you to compute A. You can compute A as A equals F over M. Very simple. And if you want to do fast dynamics, huge dynamics, large dynamics, this is what you do. All your GPU simulations for your games do explicit solvers because they're just unbeatably fast, but they come with their own caveats. So I want to discuss a little bit what it is. In OpenSees, we're used to doing this. We're used to doing the Newmark beta method. This is what us structural engineers grow up with. And eventually, so the basic idea is that you form an effective stiffness like so. Let me get a little, what's the color palette here? Why is it like this? Why don't I have a red? Anyway, let's use this brown color. So we form a stiffness matrix, and our displacements at the next time step are just computed as n plus 1 equals your k effective to the minus 1. Oops, that's a weird one. To the minus 1 times r, which is the residual, which is computed with this huge expression right here. And you have these constants that depend on the method settings and whatnot. And then once you have these values, you can compute the rest. You can compute the velocity with this expression over here. And you can get the acceleration at the step u minus 1 by doing exactly the inverse of this relationship. In OpenSees, this is what we do. And typically, if you're not thinking about it too much, which I usually don't, you set this parameter to be 1/2 gamma, and you set this parameter to be 1/4. And that gives you a nice, unconditionally stable method, which means you don't have to worry about your time step and your simulations blowing up. So that's why we like Newmark, because we don't need to think that much, and it's going to be stable. It's going to give us some nice plots, and life is going to be very nice, very nice. But what's an explicit solver? So an explicit solver, um, and before I go there, the computational burden of this is doing this inverse over here, because we don't compute inverses. We solve the system of equations typically, but this is costly for a huge model. This just grows in computational time insanely. What's the explicit method? The explicit one of the methods that are implemented in OpenSees is the explicit difference. There's another one, the central difference, which is well, different. But the main idea is this. The main idea is this. You're working, well, this is F equal ma. Like, take a look here. This is your F force. This is your acceleration, and this is your mass to the minus 1, the mass matrix over here. So we're inverting, or we're solving a system of equations which looks like this at each time step. But here comes the kicker. If you can make this mass matrix, if you can make it diagonal, if you can make it to look like this, M1, M2. Why is this so thick? Let's just go with a smaller stroke. My handwriting is really bad. M1, M2, and so then this you can fly with this. This can be done really, really fast. Whereas in Newmark, you can't get away with a diagonal K. Well, you can try, and there's a nice blog post by Michael Scott on this topic, but you usually can't get away with having a diagonal K. Whereas you can pretty much get away with this in dynamics. You can lump a mass matrix, which is cool. So then in OpenSees, this is well, this is not very well documented. I'm going to be documenting this all this framework in the coming months, but you use the explicit difference solver, and it comes with some caveats. But here's one of the important things. Like the problem here is that delta t, it can't be anything. Like it's this is a conditionally stable method, so it's conditionally stable method, which means your delta t, which means that your delta t has to be less than or equal to delta t so-called critical. Otherwise, everything explodes, which is not nice. And your critical time step is given by this little formula over here. So 2 over omega, where omega is basically some frequency, or the highest frequency of your model. Basically, you can think of it that way. The highest frequency that's going to be represented, and that means different things in different contexts. So I don't want to get too much into it, but it's basically 2 over omega, and you have to be really careful with this. If you're applying damping, this little function over here can go to 0 really fast, dragging your critical time step down to 0. So you have to be a little bit careful if you're doing something like Rayleigh damping, like this. Rayleigh, that's how you, or Raleigh. I've seen several pronunciations on this. Okay, so the promise here is that if you're doing explicit difference, you can get away with a diagonal mass matrix, and you can solve this stuff very, very, very fast, which means you can go big or go home. So what I want to show you is the results of a scalability study that I did on this same problem using OpenSees. And this is what that looked like. So I am doing a weak scalability study. I'm starting with a beam, which is a cantilever beam like this. It's fixed in the back here. And we have around 11K elements, 10K, 11K elements to start with. We want to go huge. So we're never going to model a beam with this amount of elements, but we're trying to go big here. So this is our base case. So we run this, and then we're going to compare what happens as we add processors, and we use the different methods. So basically, our setup is going to be run that using Newmark with MUMP's system of equations solver, and critically, we are going to be using this linear algorithm because it's a linear problem that we're trying to solve. And we're going to be using the factor once option here in the algorithm, because we want to go fast, right? So even we want to be fair to Newmark, we want that, remember, we need to do k to the -1, and we want to factor this matrix. Depends on what the method does, but one of the steps might be to factor it. So you can remember that you can do k equals lu, like this is the basic lu factorization. You want to have l and u, and you want to do that once, which is expensive, and then you want to reuse stuff. Anyway, this is a little intricacy, but if you want to go fast, use factor once if you can get away with it. And you can get away with it if k is not changing, and k is not changing if the problem is linear. And for the explicit difference, we're going to be using some undocumented things inside OpenSees. I recently sent a pull request to OpenSees adding this option for the MPI diagonal method. So basically, you can set a system to be your system of equations to be diagonal. But if you want to do parallel, you need to use MPI diagonal. The diagonal system of equations does have a lumped option, which does automatic lumping for all your elements. You don't need all the elements to define your lumping, or you could do it, like each element can provide its own lumping. But if you don't have that, which is the general case, you can use this option to do auto lumping of the mass matrix. And I recently added that option for the MPI diagonal solver, which is the one that we need to go big, to go huge, to go parallel. Okay, so that's the idea. So what's the weak scalability study? We run this with one partition on one processor, and we look at the time it takes with Newmark method and with the explicit difference method. Then we go to two partitions like this, and look at the way I'm doing it. I'm adding two partitions, but I am also duplicating approximately the number of elements. So we want to keep the problem size per processor core to be roughly equal, so that we're seeing how the problem is scaling. As with like if we add compute, we also add we also grow the problem size, and that way we can see the scalability of this to really large problems. Okay, then we go 4 partitions, there we go 8 partitions. So we're keeping the number of elements per core the same, approximately 16, and we end with 32 and 64 partitions. This is a beam, like it's fixed here, and I'm letting this, so I'm not caring about what the physical meaning of what's going on here. I just want many elements fast. So the problem is changing each time. It's growing in a sense, okay? So we're not going to look at the solution of the problem. We're going to look at the performance of OpenSees. So here is a first plot, and this is very, 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 very revealing and interesting. So here's what you see. In the blue is Newmark, and in the orange is the explicit solver. It says explicit Bade because I was using my own custom algorithm there. But the point here is, look at this. For a problem size of 4 and beyond, explicit Bade just stays the same amount of time. This basically doesn't, if you add more elements, but if you add more processors at the same time, you don't spend more time solving it. This is huge. And then you can see the slowdown. So the slowdown basically means you take the time it takes in your large problem, and you divide it over the reference problem, basically. So n cores over time it takes with n cores. Let's call that t with n processors, and we divide that by t1. So basically, if we use one processor, and so you see the slowdown. The lower this number, the better. Right, and you can see Newmark is just blowing up in terms of slowdown. It's beyond 10 times slower than what it started, whereas explicit methods is less than 2. There's some performance hits, but basically it's running really fast with explicit. And as I move towards 32 processors, I'm starting to use in my cluster more than one node, more than one computational node, so more than one computer over the network. And you can see here, there's no plot for Newmark because I was not able to go with Newmark all the way up to 64 processors. Check it out. But this is really, really, really good. Newmark versus explicit method. In terms of memory, look at memory. Look at what Newmark's doing. As you grow in the amount of processors, the memory usage just blows up. And what I have there in my dashed line is my computer cluster. What's the memory available, as how that grows with the number of cores. So if I go beyond this, I don't have enough memory to run Newmark and explicit. And then down here is the memory usage. You can see explicit is just not using memory at all. Like we're in OpenSees, we're using like our memory usage is all in the system of equations. In this case, we're doing linear analysis. So if you're doing something fancier like nonlinear constitutive models, then your elements or your Gauss points are going to start storing more memory. But already your system of equation has a huge impact in the memory usage. And then the last plot I wanted to show you here, or maybe not the last one, but the memory per degrees of freedom. So this is useful because it's not per processor, it's per degrees of freedom, and you can see what explicit Bathe is trying to do compared to Newmark. And there are some ups and downs to this, but basically explicit algorithms just don't use memory at all, not at all. This is a per processor, so each color line here shows the memory usage of different threads running in 4 nodes and 64 processors. So it's like 64 lines here, and you can see this is plotted versus wall time. Okay, so we can see up here the total system available memory, and if you add all these lines up, you get this other blue line over here, and basically you run out of memory after some time for this 4-node 64 process, which is the last point here in this plot, I guess, the 64 one. That's how much memory you're using. And this is the explicit method. It just does not grow. It just does not grow. So explicit methods are what's gonna drive basically HPC for the years to come. I think the really large models are gonna be explicit. We need to learn a whole bunch of things before we dive into this. We need to learn how to do statics, and this is a solved problem. This is not cutting edge research, but it just goes to show you, like, if you want to go high fidelity, you need explicit solvers. Abacus solved this, LS-DYNA solved this. These are all explicit, or if you're into soils, FLAC also uses explicit, and this is the reason. It doesn't use memory, it's super fast, it's super scalable, and we're set to go. So this is what I'm going to be working on this next year and the years to come, because I want to go again to really large models so we can do high fidelity modeling. So join me in the years to come with the explicit solvers. I think we're going to have a lot of fun. See you later. Have a really happy new year.